All right, let's get started with Lesson 7, Half-Life. To begin our discussion of half-life, let's go ahead and define what half-life is. Essentially, by definition, the half-life is the time required for the concentration of a reactant to reach half its initial concentration. Right? So again, the time required for the concentration of a reactant to reach half its initial concentration. So when we talk about half-life, we must think in terms of time and concentration. For example, if we have a first-order chemical reaction and we graph the data of the amount of concentration lost over time, so concentration on the y-axis, in this case, the concentration is going to be moles per liter of our reactant over time. And this is a first-order reaction, as you'll recognize the first-order reaction curve there, where initially the concentration is really high, so therefore the reaction rate is fast. But as we begin to lose reactant concentration, the rate of the reaction begins to slow down. So the rate law for this reaction is equal to K, the rate constant, times the concentration of a reactant. This is the only reactant, N2O2, to the first order. All right, and it looks like we're going to, according to this graph, we're going to start out with a 1 molar concentration of N2O2. That's the initial concentration. And then the time that it takes for half of that concentration looks like it's going to be roughly, I would say 52 seconds for half of the initial concentration to turn into a reactant. So that 52 seconds is known as the half-life for this reaction. 52 seconds. All right, so every 52 seconds we should see the remaining half of the concentration basically turn into reactant, and it should be cut in half every 52 seconds from there on. So after what we call the first half-life, there should be 1/2 of our reactant remaining, or remains, 1/2 remains. And then after another 52 seconds, we get our second half-life, and we have 1/4 of our reactant concentration remains after the second half-life. And then we go through another 52 seconds, and we hit the what is called the third half-life, and 1/8 of our reactant concentration should remain at that point. So every 52 seconds, we're going to cut our concentration in half, and that should then diminish the amount of reactant concentration by half every time. All right, so that's how a half-life works for a first-order reaction. And the good news is for AP and IB, they're only going to focus on first-order reactions and half-lives for first-order reactions. Now we can actually put this into an equation, and we can calculate the half-life based on the K value, the rate constant. Essentially, and this only works for a first order reaction. This equation you do not have to memorize. It will be given to you on the test. You just basically need to use it. So to find the half-life for the reaction, you take 0.693 and divide by the rate constant for that particular reaction at that particular temperature. So remember, K is temperature dependent. So they would have to say, well, at 25 degrees C, this is the K value, and then just divide 0.693 by the K value, and you should get the half-life value. All right, pretty simple. All right, let's take another look. In this case, we're going to use a decay reaction, a radioactive decay reaction, which is a first order reaction that's going to take place for cesium-137. All right, now if you look at the first order reaction here for cesium-137, how long does it take for half of our original amount of cesium-137 to decay? So if you look at the graph, it should take roughly 30 years for cesium-137 to decay. All right. The next question says how many, or after 3 half-lives, what fraction of cesium-137 remains? So this is the first half-life. We should have 1/2 remains. The second half-life, you're going to have 1/4 remains. The third half-life, you should have 1/8 remains. So the fraction should be 1/8 of the original concentration. Question number 3, what fraction of cesium-137 remains after 120 years? So we have 120 years right here. So after 120 years, it looks like we've gone through 1 half-life, 2 half-lives, 3 half-lives, 4 half-lives. And 4 half-lives would be 1/16. And so that's the fraction that should remain, is 1/16 after 4 half-lives or 120 years. Okay, question number 4. How long until less than 1% of the original sample remains? Well, 1/16, that's 4 half-lives. That's not going to be less than 1%. 5 half-lives, which be 1/30 seconds, would not be enough. The next would be 1/64. That's not going to be enough. The next is going to be 1 and 1/28. So 1 and 1/28 of a fraction. That comes out, if you take 1 divided by 1/28, that should equal 0.0078, which if you multiply by 100, that should be essentially less than 1%, 0.78%. So it should take about 210 years for cesium-137's original concentration is less than 1%. All right. The last question is how long will it take until 1/4 of the cesium-137 remains? So 1/4 should be roughly 60 years. All right. So there's kind of how you deal with half-lives for a chemical reaction. Some reasoning using a half-life graph that you see for a first order only. Or we may use the equation that we looked at before, where you actually calculate the half-life, again using 0.693 divided by the rate constant K for a first order reaction only. All right, so that is it for this lecture video on half-life. Make sure that you can read a half-life graph for a first-order reaction, and determine the half-life of a first-order reaction from the graph, and or use the equation for a first-order reaction to determine the half-life if they give you the rate constant. All right. You should be also thinking about this. You should be able to find the rate constant K for the reaction if you're given the half-life, and throw it into this equation. All right. So that is it for right now.